excellent series of lectures, and I thank once again our distinguished lecturer. Now we go over into another stage of our discussions, namely the series of public lecture. Perhaps, as you know, TÜBİTAK Research Institute for Fundamental Sciences organized public lecture series with participation of the leading scientists of our country and of the world. The aim of these events, public lectures, is to share the passion for science with a wide audience, as well as to foster scientific curiosity and scientific culture in the society. We lively stream these lectures through the social media channels of TÜBİTAK just now. As part of this lecture series and using this spring schools on quantum photonics, Professor Vahid Karimipour from Sharif University of Technology will give a great public lecture, which has a title, A Short Review of Cryptography from Ancient Times to the Modern Days. So, Professor Vahid Karimipour and the great public lecture, a brief review of cryptography. Vahid, please come.
Do you hear me? Okay. I once again thank the Institute and Enigma for its kind invitation and giving me the opportunity to come to Istanbul and see this beautiful city. Actually, when I searched for the photos of Istanbul and put on my slides, there were so many beautiful pictures that it's difficult to choose. Yeah. As Adikram said, I want to give a brief review of the history of cryptography. Maybe we can dim the light here. Is it possible? But let me first make an announcement. Since this is a public lecture and it will be broadcast perhaps on YouTube, and maybe some officers in some embassies and consulates see this, I want to announce that I am not an expert in cryptography. I do not work on cryptography. It's just a matter of interest in history, and I thought that for a public lecture, this topic is suitable because most people are interested in these topics, and it's not a technical. So, in this lecture, contrary to the other lectures that I gave, we are not doing science, it's some sort of detective story. So we can collaborate with each other to go through this history of cryptography and see how far we can go. Cryptography has developed from ancient times to the modern day. And each era of history has a name for this technology or for this affair. The Caesar era is the era where people used Caesar Cipher or Caesar Cipher. It's quite simple. You want to communicate a text or a message from here to somewhere else. And you want that nobody understands your message. So you have to encrypt your message, right? So that the message is confidential between you and your friend. The Caesar cipher is quite simple. You just transfer these letters. For example, instead of A, you write D. Instead of B, you write E. Instead of C, you write F. So after that, your meaningful sentence becomes something of a meaningless sentence. Nobody can understand what you have said. So if you write this famous word of Caesar, veni, vidi, vici, you know this in Latin? Then it becomes this sentence, which is completely meaningless. Unless somebody understands the key. The key here is how many words, how many letters this has been displaced. In this case, 3. So if somebody tries and goes back by 3 letters, he will understand what is the meaning of the sentence. What is the number of all possible keys? In this case, in this English language, it's 26. So he will try to move, to displace the words. By 1, the sentence becomes meaningless. By 2, again, it's meaningless. He tries 3, then he recovers the sentence. So the number of possible keys in this simple case is 26. It's a simple code. It's a simple cipher, right? But for that time, 2,000 years ago, it has been quite mysterious and ingenious. So as time goes on, the system of cryptography progresses. You have to make more complicated keys so that it's difficult for people to decipher the key, right? Let's go on. Here the number of keys is 26. Now we go to the substitution cipher. The substitution cipher is that you completely scramble the letters. As you see by these arrows, you completely randomize the letters. Now what is the total number of keys? Because you are making substitutions and you are making all sorts of displacements, right? How many different keys you can invent? It's now much more. How many? It's 26 factorial, right? Because the number of substitutions is 26 factorials. And nobody can guess, nobody can take a cipher text that you have transferred from one place to another, call it if, for example, to see the cipher text and try 26 factorial combinations. It's completely out of question. So this has been a very successful cipher system for 1,000 years in the course of history. Nobody could break this type of key. And at that time, there were many sorts of communications between local governments, between local companies, not companies of the old time, I mean the Middle Ages, between this prince and that prince. And so they used this type of cipher for 1,000 years. Of course, in any crypto system, the key should be common between you and your friends, or your company. You have to have the same key, otherwise you cannot communicate, right? How the cipher system was broken after 1,000 years? Can anybody guess?
Frequency analysis.
Exactly. And do you know who?
I'm not sure.
This crypto system was unused for 1,000 years, over 1,000 years. And it was broken by this Muslim or Arab scholar, Al-Kindi. And he used the frequency analysis, try to decipher the text by using the frequency of the letters. For example, if you receive a text, which is an English alphabet, and you see that the letter Z, for example, has been repeated many times, much more than the other letters, you guess that this is not the real Z. This is the letter E, because in the English language, E is the highest frequency letter. And then, by just one word, you try to decipher the other words, right? So by one frequency analysis, you can decipher this very complicated cipher system. In fact, now you can use the frequency analysis for letters, even for syllables of letters, 2 letters, 3 letters, and so on, and decipher this type of cipher text. It has become easy. by frequency analysis, we can decipher this type of cryptic system. We have to progress to more complicated keys. How we can design more complicated keys? We should design keys so that all the letters will appear with the same frequency. Then no one can break this type of cryptic system. No one can see any irregularities, right? Because all the letters appear with the same frequency. This is called polyalphabetic. In a simple form, it was designed by Leon Battista Alberti. It's called polyalphabetic cipher. It means that, suppose that you have these letters, A, B, C, D to Z, then you do two kinds of substitutions. One from this one, this row, and one from the other. This is the two alphabetic systems, right? And what do you do? For example, suppose that this is our alphabet, and I use this substitution and this substitution alternately, one by one. I first use row 1, then row 2. 1, 2, 1, 2, these two rows. And if now I want to decipher a word like Ankara, right? For the letter A, I use the row 1. So this is cipher to X and something else. The second A, I use the second row. A is cipher to G. And then this A is ciphered also to G. So A has been ciphered either to X or to G, right? Because I'm using two kinds of substitutions. The same letter has been ciphered to different letters. And then I cannot use frequency analysis. But we can do better than this. Instead of just two rows, I can use 26 rows, right? And one by one, I use these letters, right? These rows for ciphering the text. But note that these are really simple substitutions, but just translations, right? Transfers. The first row by one letter, the second row by two letters, the third row by three letters, and so on and so forth. And I can use a trick. What is the trick? The trick is that the order of the rows that I'm using will be random, will be the key. In which order of the rows I'm using these substitutions. For example, this sequence of rows is my key, which is common between me and my friend. I use this kind of rows, 1, 3, 5, 3, 4, 9, etc. This random number of keys, rows in this table that I have. And instead of communicating these numbers between me and my friend, which may be complicated, I use a sequence of letters, meaningful letters, which encode this set of numbers in the rows. And the letters is our school is in Istanbul. What it means? It means that I go back and I search the word our school is in Istanbul. Our is from this row. So for the first letter I use this row. Then for the second letter I use the row which begins with U. And then with the third row, the third letter with for this row, and so on and so forth. So we have a meaningful key which is common between me and my friend. And according to this sequence of letters, I use this table and communicate the words. It now means that I'm using each letter exactly with the same frequency. Exactly with the same frequency, I'm using these letters. And now frequency analysis can reveal what I'm doing. We can stop now for question if there is any question. Any question up to now? Is it clear? Right? Even now, you can see some regularities. I told you that this is a detective story, right? So we will try to see if there's some regularities in this type of text, cipher text that we receive. We want to see what is the real message. We look at this, it's completely meaningless. All the letters have the same frequency. You cannot do any type of frequency analysis. Letters A, B, C, D, E, etc. all have the same frequency, right? So the method of alchemy doesn't work. But again, you can see some regularities. If you look at this text, it has no meaning. All the letters appear with the same frequency, and it appears unpredictable. Nobody can predict this. But again, we should do our best. Let's see how. We can see some repetitions. How we can see some repetitions? You look at this text, and you see that some expressions, M-U-E-T, which is meaningless, but it has been repeated here and here. Or a sequence of words like E-K-T. You can see this here and here. Why? Why such repetitions occur in this text? What is the origin of this? What is the secret of this? You can see why. What do we understand from these repetitions? The point is that the key may be accidentally, the same words of the key may be accidentally in the same place of the text. That causes repetitions. So, if we have this text over here, and now we have a school, and we are playing some games, etc., then our cipher text, our key is here. Is Istanbul, is Istanbul. And accidentally, this is Istanbul, and this is Istanbul, are below and. So then you will see O are you here, and O are you here, Q are you here. This is because the same part of the key appears below the same part of the cipher text, and they code into the similar, still meaningless things. And then we will see repetitions. So what do you understand from this? So what? What we understand is that this L, the distance between these two similar and identical words, is perhaps a multiple of the length of the key, right? You will see this. And then you try different phrases which are similar to each other. You calculate the distances between these phrases, between these identical phrases, and you will see that, for example, this has been repeated, and you calculate the distance is 5. You see another one, this one, has been repeated. The length of this is 95, right? And 95 is a multiple of the length of the key. 95 is factored to 5 and 90. So the length of the key is either 5 or it's either 90. But then you see other repetitions. You see this one, whose length is 5. Or you see this one, whose length is 20. If the length is 20, it means that the length of the key is either 2, or either 4, 5, 10, or 20. And you also see this one. Then if you are the detective, you want to cipher this text, what do you guess for the length of the key? What is your best guess? What? 5. Because 5 is common to all of these. Right? So, you discovered the length of the key. What do you do then, after discovering the length of the key? You do frequency analysis. 5 by 5, you chop the text and you do frequency analysis. Because all of them had been ciphered by the same key. This is the monoalphabetic substitution, and you do the frequency analysis. And you decipher the key. So once you have the length of the key, we use the Alkindi frequency method to decipher the text. It's easy. During the course of history, this system has been in place, but it was discovered by this method that I explained to you, how it can be broken. Then it came to World War II. The World War II is the climax of all this efforts for ciphering and deciphering, right? And in fact, history tells us that the attempt to decipher the keys of the German allies saved the life of perhaps 20 million people. Let's see how. This guy invented the Enigma Machine. How the Enigma Machine works. You have heard about the Enigma Machine. It's very famous. What is it? How it works? It's a machine like this, like a typewriter, right? And the final point is that you type something, and then something else comes out of this, but in a very complicated way. The way that works is that each time you stroke a key, the machinery, the wiring, and the wheels, and so on, and they change, so that the next time that you are typing the same key, something else happens. So it's a completely polyalphabetic crypto system. How it works? From here on, you have to be much more attentive and careful. How it is possible? These are the keys. This is the keyboard. I'm writing a simplified version of this. This is the keyboard, right? And this is the scrambler, which scrambles the letters by all this wiring. It makes a substitution, and this is the line, right? So you type A, but the output is B. You type B, but the output is A. You type C, the output is D, etc. This is the action of one of these wheels. One of these wheels is doing this kind of substitution for the simple alphabet that I've written there. But you have three wheels, not just one. There are three consecutive wheels which are scrambling the letters. Then you can say that but the combination of three wheels at last does one substitution. So why we should care about having three wheels? You have three wheels, they are wiring to each other in a random way. The outcome of these three keys, of these three wheels, is just one substitution. Why do we care about three wheels? What is the point? Any guess? Act like a detective. What is the action of these three wheels? Why not just one wheel? Because all these wiring are random. The point is that when you strike a key, the wheels rotate and the combination will change. So combination of three wheels, since they are not static, it's not equal to one wheel. Because once you stroke the key, the wheels try to rotate and everything will change. Okay, that's the point. These are the wheels. Here is an Enigma machine with more than three wheels. It has four wheels. But with any number of wheels, you have some rotation of the keys. It's like that, it's as if you are writing with a million number of typewriters. Let's estimate or calculate what is the number of keys, the total number of keys here. The number of keys up to now is 26 times 26 times 26 times 3 factorial. 26 is the number of position of the first ring. 26 is the number of the position of the second ring, because I can tune it. The starting point to be on A, or B, or C, and D. Times 26 times 3 factorial. What is this 3 factorial comes from?
Order.
The order of the wheels. I can interchange these bits. So the total number of keys here is this number. 10, 54, 56. Right? We can say that it's not a big number. I can break these numbers easily, but let's wait. So we have a substitution. This part does the substitution, these parts. And this reflected does something else. Then we have, at the end, we do something different. At the end, we choose 12 of these words, 12 of these letters, of these wires, and they be interchangeable, 2 by 2. How many ways we can choose 12 letters from 26 letters? By this number, right? So after all this scrambling, we do these substitutions again. So by this total number, we can choose this 12 numbers, 12 points from 26 points. And then, it's again a very simple combinatorial task, combinatorial problem, to find the ways that you can substitute this. If, for example, you can choose this one, and you want to substitute it with one of these red ones. The red ones are the ones that you have chosen by this number of ways. Now you choose this one. You want to substitute this with one of these. How many ways you have? 11. Because you have 12 red balls. You choose one of them, the first one, and you want to interchange it with one of these. You have 11 ways. Then 9 ways. Then you have 9 ways, 7 ways, and this number. So in total, the number of keys up to now is this number times this number times this number. This was the number of ways that we could arrange the wheels. This was the substitutions, and the total number is 10,000 million billion. This is the number of keys that the Enigma machine has. Now, when you communicate, the point is that you should not do any repetitions. Let's see how this works. You have a booklet which is common between you and the receiver. And this booklet has the keys, because the keys should be common between you and the receiver, right? The key should be common between you and the receiver so that you can know how to communicate with each other, right? So you have a table of daily keys, day 1, day 2, day 3, day 13. The order of the wheels is written here in this daily key, this booklet. On the first day, you have this order, 1, 3, 2. On the second day, you may have another combination. On the third day, you may have another combination, right? And then the wheel setting. What is this wheel setting means? It means that the first wheel has been set to Q, the second wheel has been set to W, the first pin, the third wheel has been set to B. This is the combination of the wheels. And then, this is the substitutions. The substitutions which comes from those 12 alphabets, 12 letters that I choose to interchange. So each day has a unique key. It consists from these things, right? I can choose this by 6 factorials, and I can choose this by O n. Any guess? Q, W, and D. The first field, I want to choose the first field, 26, times 26, times 26. And this one's, how many ways? I have to choose 12 letters from 26. It is the combination of this. Right? It's a huge number. But These are the ways that you choose these letters, right? Then you have to substitute 2 by 2 these letters. It is times 1, 11, times 9, times 7, times 1. This is the number of substitutions. So each day you have this number of keys, and you have to have a common key between you and your friends. And you should not go to your friends and every day see this. So you set a common key for 1 month, right? And you and your friend agree that on the first day, the arrangement of the wheels is 1, 2, 2. The arrangement of the letters of the first letters of the wheels are Q, W, B. And the substitutions of the first day are this. The second day, all these will change. The third day will change, and so on and so on. We are okay? Right? And what was the number of all these combinations? For each day, we had an estimate. 3 factorial, 6, times 26, times 26, times 26, times this number. What was the total number? Approximately 10,000 million, right? In each day. So this is our crypto system for Enigma. You have a machine of the type Enigma, and your friend, or the other part of the army or whatever, they have the similar machine, and you just try to set your wheels according to this combination. You just plug in the letters according to this combination, right? And you choose the order of the wheels according to this column for the first day. For the second day, you change everything. Your friend also changes everything according to the same row of the table, and you do combinations. So there's a huge number of keys, and this crypto system is polyalphabetic. All the letters appear with the same frequency because the wheels are always rotating. So it is as if when you are writing the first letter, for the first stroke, you are using one typewriter. For the second letter, you are using another typewriter. For the third, you are using another typewriter, and you have 10,000 million typewriters for writing a message, one by one. Can this system be broken? You promise to act as a detective, or I ask you to give such a promise. Can the system be broken? Any clue?
Yes.
Yes, with the tone of question, yes, and with the course of history, yes, we can say that, yes, it was broken. How it was broken? This is a fascinating passage in our history, how it was broken. Repetition is the enemy of secrecy, right? You should not have any sort of repetition, any sort, at all. Let's see how. Even if you are using, for the first day, one row of the table, in one day, you are using many messages. You do not want to communicate only with one message. Suppose that there is a war between Germany and France. In each day, Germans have to convey thousands of messages. They cannot change everything. So they use the same row after, for example, the day 14, and they use that row for communicating thousands of messages. So there will be repetitions. But all these thousands of messages are polyalphabetic. They have the same frequency. And the number of keys in each day is this huge number, 10,000. But again, there is repetition because you are using one row for many messages, right? How this can be broken? Let's see. you have to have a code for each message. So for the first message, for the second message, and for the third message, you write a code. For example, for the first message, I write a code SAD. For the second message, I write TNE. And for the third message, I write RSU. What are these three words for? How do I use this? I use this to convey the order of the bits for that message. So I change the order of the bits even for one single message. There is a key for each day, but for each message, for each single message, I order the order of the keys. Not the order of the bits, because it's a difficult mechanical thing. I just use plugs to change the first word, to change the first pin. So instead of, for the first message, I use these pins, SAB, and for the second message, I use these pins, right? For the third message, I use these pins. In this case, I avoid repetitions. So let's stress again. For one day, there are many, many messages, right? These substitutions do not change from message to message. The order of the bits do not change from message to messages. It's difficult. But the order of the first letter of the letters in each wheel changes. Suppose that this is the starting point, right? I put here the word, for example, S, A, B. This is just an electronic thing. For the second message, I do such that instead of S, A, B, there will be T and E, right? For the third message, I use R, S, U, and so on, and so forth. So for each day, for many, many messages, you use many, many different things, right? Then you avoid repetitions, okay? Are we happy? No? As cryptographers, we're happy. Okay. But how do you inform the receiver from these keys? You have to use the daily key. For the daily key is QWB, right? This is the daily key of one fixed day. You have the same key, QWB. For that day, this is fixed, but the order of these three letters for each message changes. So you encode this SAB with this one, and you write R and S at the beginning of this message. These three letters at the beginning of this message doesn't convey any information. It just says that what I have used for the three letters, right? So the receiver knows that these three letters do not convey information about the content of the message. They just say that what are these letters? And then he tries to decipher them. For the second message, I use T and E. This is encoded to Z, T, B, etc. And then the receiver knows that what are the orders or the combination of these letters. But maybe there will be some errors. Today, this morning, we talked about errors. If there's some error in these letters, the whole message will be destroyed. Right? You agree? If there's some error in one of these letters, the whole message will be destroyed, and nobody can understand this. And it's very sensitive. These are not friendly messages. They are important messages. So there should be no error. So how do we do to prevent this error? they repeat the 3 letters, right? So instead of SAB, one SAB, I write 2 SABs. It's natural to avoid errors. And then, do you agree that the message will be like this? The message that I receive from my friend is like this. So I see that 2, 3 letters have been repeated, RMS, RMS, and I understand the order of these pins. Do you agree with this one? Why not?
Can be different.
Sorry?
I mean, it can be understood.
No, I mean, if this system works like this one, I'm using SAB and repeat this 2 times. I want to see if what the receiver receives is like this one.
The machine is rotating.
Exactly, no. Because the machine, the wheels rotate, you will not see this one, right? You will not see this one. You will see this one. So instead of 2 RMS, 2 identical RMS, you see 2 different things, 2 different letters. It's complicated, right? So you cannot understand what is these 3 letters because they are different, right? But again, repetition is the enemy of secrecy. We should not repeat anything about it. And this is one of the fascinating passages in our history. It was discovered by this great Polish mathematician, Marian Rajewski. And he noted a regularity, a very interesting regularity in these patterns. He noted that this is the statue of Rajewski in Poland, and this is the model of Enigma. This is Rajewski himself. And he noted this regularity, that also these letters are not the same. You see that these 2, 3 letters, these 2 sequences, they are encoded into 2 different things, RMS, PAL. Then, for the next message, these QZT, QZT encode to different things. For the third message, the same thing happens, right? But after all, if you look at all these messages, you see some regularities. You see that, for example, R always comes before P, or G turns into Q in the second sequence of letters, or N goes to R because of this combination of wheels, and you will see some patterns, right? R goes to P, G goes to Q, N goes to R, etc. You see these cycles, so you store these cycles on some papers and some thing. And you think about these cycles. He understood that these cycles tells us something, so you write all the cycles that appear in the ciphertext, and you will see that the length of the cycles, this is the mathematical argument that Rajewski and his group followed, and it was an important contribution, that from the length of these cycles, you can decipher the combination of the fields. This is the important contribution of Rajewski. The patterns of the cycle and the length reveal the combination of the fields and the way they have been set. So they say that which of the fields have been set, 1, 2, 3, or 3, 2, 1, etc. So we divide by 3 factor by 6. And you can also divide these, the total number of keys which were unknown by 26 times 26 times 26. Because this pattern of cycles reveal the ways that these fields have been set. So the number of keys that you have to search reduces drastically. Once the setting of the wheels is discovered, the task becomes much easier, also still highly difficult, non-trivial. And this is the model of the computer that apparently was used at that time, World War II. But then, in the last stages of the war, and World War II, the number of ways increased from 3 to 5. Now the matter becomes much, much worse. Because instead of this rather small number, 26 to the power 3 times g factorial, you have 26 to the power 5 times 5 factorial. So this number, which was rather small, it was 1 million, became suddenly 130 billion. The total number of keys now becomes 130 billion. And nobody could decipher this number of keys. It was the contribution of Turing, who at that time had developed the concept of computer that we talked about 2 days ago. And they set up in the facility named Bletchley Park with hundreds of mathematicians, chess players, even priests, and at that time, computer scientists of that time, to make a big computer so that they can use the Rajewski method and the Rajewski contribution to solve this problem, to decipher the Enigma cipher. And with this contribution, it's estimated that they shortened the length of the World War II by 2 years, which means that they saved the life of 20 million people, at least. This is the picture of Klaus's computer from that time, but this computer was then dismantled. It doesn't exist anymore. So we have to avoid repetition of any kind. This means that you have to, if this is your message, a sequence of zeros and ones, you have to have a random key of the same size with no repetition. This is your message, this is your random key, and then you add them one by one, and you find a random sequence. This is your decipher text. This is your main text, this is your key, this is your cipher text. Now the point is that how you have to communicate this key, because the key should be common between you and your friend. How do you have to do this? How do you communicate the key? How do you have to do this? Any idea? After all, for any communication, we have to have a common key. How do we do this? We use another key, right? Do you agree with this?
Reverse the key.
Right?
Reverse the key.
Sorry?
I reverse the key. I reverse the key.
A reverse key. What do you mean by reverse key?
Which reverses the key.
Oh, but it should be common between me and you.
Yeah.
And how we agree on a single key. That's the question.
So they want.
We should meet each other thousands of times in each day. It's impossible. Right?
Should we send the key to message?
So we have to send the key to a message. But again, we have the same problem. Because there may be some errors. Then we have to repeat. And you know that we have to avoid it.
Can we integrate the key inside the message?
Sorry?
Can we integrate the key inside the message?
Yes, that's the same thing that your friend suggested. If you integrate the message inside, the key inside the message, there may be some error. Right? That error completely disrupts the message. If you want to avoid error, you have to repeat it. Repetition is not allowed. You noted that even for one repetition of 3 letters, allowed Rajewski and Turing to decipher the enigma. Even one bit should not be repeated. So how you agree on a single key? You want to send a message from Istanbul to Ankara. Your friend is in Ankara. How do you agree on a single key? The key is a random sequence of bits. So you meet each other in Izmir for every message, What's the point? You can live in Izmir and then communicate the messages. Any idea? This is called the one-time pad. The key should be of the same length as the messages. They should have the same length to avoid repetitions. But it appears that this is a problem with no solution. In fact, it appeared till 1970 that this is a problem which is called key distribution. And it appeared that this problem has no solution. So we cannot do secure communication because of this problem, which seems that it has no solution. Right? But 1970, it was found the solution. The solution was found by two computer scientists. The solution is called public key system. And the public key system is like this. Here you have two people, Alice and Bob. It's called, the modern version is called RSA system. Alice has two keys. One of these keys, this one, is public. It's a huge number. Right? The factors of these numbers, PA and QA, are secret for her. So Alice takes a huge number, 100 digits, for example, and this number has two factors, right? So in A is equal to PA plus QA. This is public. Everybody knows this. But these two are secret for us. Only Alice knows this. Right? From the secret key of Alice, you can find an A, because multiplication is easy. But if you know the public key of Alice, if you know this large number, you cannot find the factors, because factoring is an extremely difficult problem. So these things, these numbers inside these ovals, they are public. Everybody knows. But these factors is secret to Alice. The same way is for Bob. Everybody knows the large number of Bob, but nobody knows these two factors. Right? Now you do this one. Alice wants to send a message M to Bob. Right? She uses the public key of Bob, NB. Right? NB is public. Everybody knows it. And she ciphers this M to M prime. It's a mathematical scrambling of this number to this number. It is used by NB. And sends M prime to Bob. Bob knows his own secret key, QB and PE. And again, uses a mathematical algorithm to turn M prime back to M. Right? And there is no need for Alice and Bob to meet each other. Right? This is called public key system. We just use the public key of your receiver. Alice uses the public key of Bob. Right? But how Bob should be sure that Alice has sent this message? Anybody could send this message. Suppose that, for example, the message is that, Bob, please give $10 million to Charlie. Anybody can send this message. Right? Not Alice. Bob has to authenticate the sender. Bob has to make sure that this is Alice who has sent this message, not anybody else. How is it possible? Any idea? second stage. Alice uses her own secret key, PA and QA, to scramble this message again, n prime to n double prime, right? And sends m double prime to Bob. Now Bob uses an A, which is public. Everybody knows the public key of Alice. So Bob uses NA to decipher n double prime, first to n prime, and then uses his own secret key from n prime to n. So they are not required to meet each other. And they can authenticate the sender, and they can cipher and decipher the message. This is the public key system, which has been in operation for more than 3 decades perhaps, more than 5 decades. And now the communication is based on this system, and it's unbreakable. Right? Do you believe that it's unbreakable? Do you believe? If a quantum computer is made, then factoring will be easy. If a quantum computer is made, then you can look at the public key of anybody, you can find this big number and factor it, and find his or her secret keys. And then all the communications become transparent to everybody. Everybody knows communications, right? So if there is a quantum computer, then our present communication system will be destroyed. For that, we have to resort to quantum methods, to physical methods. In fact, there are 2 main shortcomings with this present RSA system. The first shortcoming is that it depends on mathematics. In the progress of mathematics, maybe some algorithm will come who can break these large numbers, right? Mathematics is not this sacred thing. People work on different algorithms, and maybe they will be able to break the code, break these difficult problems, to factorize numbers. And the second thing is that it's not safe against future. It doesn't have future secrecy. What it means to have future secrecy? Suppose that I am a government and you are the enemy. I just gather your communications and store them somewhere. Okay? And when mathematics develops, I find the secret message. I go to your messages for the present and decipher all your messages. And I will see that how you have thought in year 2023. We are, for example, in 2015 or 2015. I look at your messages, your communications in 2023, and I find something about your policy, your future, your plans, and so on. So this doesn't have future secrecy, the present system. This is the main 2 shortcomings of the system. It depends on mathematics, and it's not safe against future. So we have to develop a crypto system which is entirely based on rules of nature, not mathematics, the nature laws. For this, we have to do quantum cryptography, and I think that Angelo will talk about that. So I leave it here, and thank you very much. Any questions?
Thank you very much for this very nice lecture. Since we have no much time, a couple of short questions.
Yeah.
Thank you once again. Let us please. Before going to lunch, let us please